Our next speaker is Håkan Hedenmalm from KTH, and he's going to be talking about Hyperbolic Fourier series. Go ahead.
Thank you, Bill. Is that you finished, Bill?
Yeah.
Okay. So I will tell you about something which is a new topic, more or less, which never never developed in the past. So I will tell you what it is because you don't know it. Okay. So, but first, before I give you the topic, let me tell you that it's joint work with an equipe of people. We are 5 altogether, and it's Bakan, Montes Rodriguez, Radchenka, and Vyazovska. Okay, so 3 Ukrainians, 1 Spanish, and 1 Swede. All right, let me tell you somehow about the underlying thinking. So we begin with Fourier series. How we usually do Fourier series, we have a period, positive period P, and the periodicity says that f of x plus the period is the same as the function. All right, now when you have a periodic function, you try to expand it into cosines and sines, or if you like, you can do it in terms of complex exponentials. And I prefer the complex exponentials because it's so much simpler. Now, what the formulas are written there, we have the function expressed in terms of Fourier coefficients, and the Fourier coefficients are expressed in terms of the function. So you can go back and forth in this representation. This is all classical and you know it very well. Now, if we have a function with period P, then it also has period 2P. It has period 3P and so on, of course. So we can sort of model it inside that paradigm of being like Kp periodic. And if you do Kp periodic and let K go to infinity, what happens in these formulae is that they become like Riemann sums for integrals. And in the limit, you get Fourier integral theory. Okay, and the periodicity disappears. All right, let me give you an alternative approach to represent functions which don't have periods. And then we replace working with the dilatations, so dilations, by another transformation. We do x maps to -1 over x on the real line. Okay, now, and then we, with respect to periodicity, we fix the period to be equal to 2. Okay, so P is now 2. And then we work with, we have the standard Fourier inversion. If you have a periodic function, it's, as I said before. But then if you start with another function G, you can move to functions that are, you insert the transformation -1 over x. And what's the relationship? If you do that, you start with G, which has period 2, and then you do this little g of -1 over x. You get a function capital G of x, which then has some kind of nonlinear periodicity because G was nicely periodic. So capital G has some kind of periodicity too, but another kind of non-standard periodicity. And then we realize that the previous relationships which occur for F, they of course occur for little g also. And then this transfers to the capital G function as well. So the capital G function will have this kind of relation. The G is equal to some coefficients times this complex exponentials, but written with -1 over x. And then we have a relationship which gives the coefficients. And I give you some idea about what happens after inversion is that those the typical periods -1 to 1 and then 1 to 3 and so on. These periodic intervals they're mapped in a nonlinear fashion so that they accumulate at the origin, all of them. And they get very short intervals accumulating at the origin. Okay? Any questions so far? Nobody? I'm sorry that I'm giving this talk apparently in this Bergman space block for you and at the Fields Institute, but this is not necessarily a matter of Bergman spaces. It's more like Fourier analysis and how to do things differently. Anyway, we start with some function capital F, and suppose it has some modest integrability. For instance, if it's bounded, it's true. No periodicity asked of it. Can we then build it using those two building blocks I told you about? So we have first the idea of the ordinary two periodic Fourier series plus the other guys, which I described in terms of the function capital G. So can we find coefficients so that this expansion is true? And what's amazing here is that it is possible, and the coefficients are unique. If you just require that you would get double representation of the constants. So you need to remove that. So you just ask the second coefficient to vanish at n equal to 0. But apart from that, you get all the functions. You can get all functions represented, no periodicity, no nothing. Are there formulas for these coefficients? Yes, there are formulas. And are they unique? Yes, they are unique. Okay. It's a bit surprising. Let me digress further a little bit. Why would you do this kind of expansion in the first place? Well, consider a function phi which just integrable on the line and produce the corresponding function, two variables, u sub phi, function of x and y real. Then you look at that expression, you stare at it for a while, then you see, okay, we take the x derivative and we get one formula, we take the y derivative, we get another expression. And what happens is that when you take the derivative with respect to x and derivative with respect to y, we recover our potential with a negative sign. So it solves the differential equation, which is written there. Second derivative with respect to x and y plus the function is equal to 0. And that equation is known as the Klein-Gordon equation. It's a prototypical, non-trivial, linear, hyperbolic partial differential equation. And what we are looking at here are some kind of standing waves then, because they are also bounded functions. In fact, they flatten down to 0 at infinity somehow. And so they're still, they have some properties of permanence. They tend to, okay, so they're built up by standing waves somehow. Next, let us look at these the values along the axis, but at integer points. And then you have here, what do we have? We have, in the first case, we get the integral, like when you calculate Fourier coefficients, only you integrate over the whole real line instead. And then we do the other one, and we get that corresponding expression. And what's interesting to remark here is that we have the uniqueness property, that once you know that those values at those integer points vanish at all the integer points, then the potential vanishes. In other words, the function phi vanishes. So in principle, it's possible to recover the potential u sub phi from the values on this lattice cross. And that is what this theory somehow allows us to do. We're able to recover the values of this potential at integer points along the two axes. Okay. Now, I told you there were these coefficients. So how to get them? In fact, it's very easy. You just integrate f against a system of functions. These functions called here h with index minus n, and m with index minus n. And what kind of properties would they have? They're smooth on the line, and then they decay in a good way. So you don't have really big problems here. I think maybe this n squared is not optimal. You can do a little bit better than that. But anyway, you see for easily that this integrability implies that the coefficients are well defined. And then I want to say something about the uniqueness. So let us assume that we have a bounded function on the real line, which has the property that when you extend it to a harmonic function in the upper half plane using Poisson integrals, you get actually a holomorphic function. Okay, then what can you do? In this case, you have f is, well, this representation I told you about. And the natural thing here now is that n should be non-negative. And then let's look at these things. Let's look at capital F, this curly f, and this curly f twiddle. Suppose that this function you started with is just the trivial zero function. Does it force this in the decomposition f twiddle and f to be zero, curly f and curly f twiddle? And we look at it, we see that the curly f plus curly f twiddle has to be zero then. And we look at the invariance properties of these two things. And then you realize that it has to be a lot of invariances. And at the same time, the function should be bounded. So then you realize that, in fact, you are dealing with a function which is periodic with respect to transformations that form a group in the upper half plane. This amounts to studying functions that are holomorphic on a Riemann surface you get by taking the hyperbolic plane modular of the group. And this is a group is such that you get cusps. That's all. And then you have basically a Liouville type theorem that since you have boundedness, you would get that your function has to be constant. And if it's constant, well, one of them would have to be zero, so they're both zero. All right. Then I want to say that there is some relationship with dynamics on the interval -1 to 1. Okay, what is this? You take the mapping x goes to -1/x. That's a mapping of the real line to itself. You restrict it to the interval -1 to 1, then, well, then you get -1/x will be, it could be quite big, but you want to keep it in this interval -1 to 1. What do? You add or subtract an even integer. By doing the right even integer, you can force it to be in this interval -1 to 1, -1 to 1, and you get a conveniently defined mapping now. And this dynamics is related with an operator which you could call T1 here in this setting. It's the Perron-Frobenius-Ruel operator associated with this dynamics modulo the even integers. And well, there are many properties here. You could easily see that it contracts the L1 norm. And it's only possible to have equality if f has equal sign. So it's basically positive times a constant. And then, well, what can I say more about these things? Well, there is a relationship here. These functions hn and mn were a bit mysterious. So, but it's related with this Perron-Frobenius-Ruel operator, and they solve these kinds of equations. You form the sum, these two sums with pluses and minuses with curly hn. And then it solves this equation I plus T1. So it's some kind of Neumann series. So hn plus is some kind of Neumann series associated with these complex exponentials. So basically we have two Neumann series representing these two kinds of functions. But this is hard to make something to obtain the properties of those functions out of, but it is nevertheless the truth. Let's see if I think I was running too quickly. Let's see. That's my problem. I was running too quickly here. Do we have any questions? Maybe I should slow down a bit because I think maybe I have a feeling I was too quick. What do you think, Bill?
It's up to you. I was understanding stuff as you went, but if you want to go back and cover some highlights or...
Yeah, maybe I should say again. Okay, so the highlights, maybe I should have done more slowly. Okay, this is when when I was writing it, and when I gave this talk earlier, it went smoothly. It was just the right amount of time. Now it's written. It's so easy to move quickly.
Right.
And so it's all becomes difficult following a smooth pace, I think. Okay, maybe I start from the beginning again, so you can get a better feeling for what I wanted to say. We start with, if we have periodic functions, there are Fourier coefficients. Okay, and then out of Fourier coefficients, we can do Fourier integrals, and that's a way to represent functions on the real line without periodicity, of course. It's a well-known theory. You can get the theory of tempered distributions and so on. So we can get a lot of things out of this. But here, somehow, it's of interest to introduce another approach. So to represent bounded functions. And I should also probably say that it's related with the notion of trying to recover a function from its Fourier transform from the values of the function along a sequence, a discrete sequence, and from knowing the Fourier transform of the function along a discrete sequence. Probably you guys have heard of that. Mm-hmm. Something like if you know that the function, do you know the values of the function along, let's say, square root of plus minus square root of positive integers? And the same thing for the Fourier transform. Can we recover the function out of that kind of data? And that's what this thing is related with. Okay? Which I didn't quite explain now, but I wanted to give some ideas of how to possibly represent functions without periodicity in another fashion. So the main key thing is this formula. Can you see? It's a formula for representing any function f in terms of some kind of two sets of Fourier coefficients. One is the ordinary kind of Fourier coefficient, and the other one is some kind of nonlinear Fourier series. Okay?
Mm-hmm.
And if we have that representation, somehow it's possible to say that these coefficients are unique, and even how to describe them. So given a function, it's possible to write down the coefficients, but of course the convergence is not so good point-wise maybe, but still the coefficients exist, and we can in principle talk about this decomposition. The only slight issue is the possibility of double representation of constants, so you need to remove that, and then you need the second coefficient f, the double hat f at n, to be 0 when n is equal to 0. Okay? So that's the condition. So this red thing here that f hat, that it should be equal to 0 is only when n is equal to 0. Okay? And then the question was, which can you do? Which f can be possible here? And it turns out you can do all functions f that are reasonable. Can we get formulas for the coefficients? Yes, there are formulas. And are these coefficients unique? And there was a relationship with PDEs. And the whole thing is quite strongly related with Klein-Gordon equation, actually, this hyperbolic PDE. And this type of solution, which is built from basically finding a standing wave and adding up a continuous family of standing waves. So maybe these exponentials are better to call them standing waves, and then adding up several by integrating against this function phi, we get a collection of solutions with a little bit smoother behavior than the standard standing waves. So, yeah. Probably you have studied at some point you studied the hyperbolic equation called the wave equation. The wave equation is when you don't have this u sub phi there. U is not there. It's just the second derivative of x and the second derivative of y of the function is 0. And now we've added this funny expression, adding u there to the equation. That then gives it tells us that the equation has a little different behavior. If you take the wave equation, you know that it looks like there is this famous formula by D'Alembert. What it means in this setting is that your solution of the wave equation without this u sub phi would be a function of x plus another function of y. Okay? And that's the whole set of solutions. And those functions don't have any good decay behavior at infinity or anything. They just you know. But here there's some dissipative behavior of the Klein-Gordon equation, which is maybe not well understood yet. Dispersive, I mean. That what I'm talking about somehow is related with that behavior. So suppose you have such a solution which it has this form, then once you assume that it vanishes on a very sparse collection of points, actually, along the y-axis and along the x-axis, you get that the function collapses if it vanishes on those points. It's just a zero function. That's very unusual. If you would take, you'd need to have it like an entire function to have such a property, right? If you have a function that vanishes on, well, Cartwright's theorem or something, if the function vanishes on just the integers with some growth control, then maybe it vanishes everywhere if it's an entire function. But here, this function is not entire. Has nothing to do with entire functions. It's not able to, you can't just plug in complex x and y here, it won't work. They're just real. And the function only solves this equation, it's not holomorphic.
Hello,
So it's
Mr. Moratz. This is Mr. Sima calling. I'm calling from my hard line 919-929.
Okay, don't worry about it, Håkan.
It's okay?
Yep.
Okay, so we have that, the vanishing here is a bit peculiar somehow, that it's possible to get from vanishing along this very thin collection of points that the solution vanishes. So it's something very rather a bit unexpected. And that is related with this representation. It just shows you that, it's related with this representation. So you could think of it like you represent in terms of sums of such expressions. So it's like dual of this. It's a dual thing to what I'm talking about. Now, and then I want these main points are that the coefficients of generalized Fourier coefficients are representable in terms of a dual basis. These functions h minus n and m minus n, which are smooth functions. In fact, I think they're maybe entire functions, or maybe they have possibly a little, well, okay, but they behave very well, and at least they're smooth on the real line and decay in a good way. So you can have these coefficients, and here also I wanted to describe. I would describe a bit on the uniqueness parts. So in fact, the main thing is how to split into the first kind of series and the second kind of series. And this splitting has to do with dynamics and, if you like, invariance. So the first function would have to be periodic, and the other one has this kind of funny nonlinear, Mobius invariance. And if they add up to be zero, the sum, then both functions have to be invariant with respect to both systems. And that means that there are not too many such solutions. So that's forces them both to be constant. And since one of them, if it's constant, has to be zero, then both have to be zero. And then finally, there was this connection with dynamical systems, which is what we discovered with Alfonso many years ago, actually now. It happens that on the dual side, that it's if you want to say that you get the complete collection of functions in this way, in this fashion, then why would it be true? Well, it's because you study the functions that annihilate all the basis elements, and then you show that the functions that annihilate the basis element, they have to be eigenfunctions for this operator T1 squared. And T1 squared, T1 is just this Perron-Frobenius ReL operator, which is a natural thing associated with the dynamics of the mapping of the unit interval. What it does, what is the mapping? It's a mapping of masses, in fact. So if you take a Dirac mass at a point, Dirac delta at a point, you apply it, you can think of the T1 as sending it to another Dirac mass at the point which is sent, that the mapping sends it to. Okay? So it's juggling around these point masses, and when you know what's happening with point masses, then you know what's happening with L1 functions by integration. And then the matter was then about invariant functions under T1 squared, and that was there were no such functions in L1 for dynamic reasons. In fact, the reason was that well, there is the invariant measure is ergodic, and it is a constant times 1 over 1 minus x squared, that which has an infinite mass. So it is in this infinite mass ergodic theory. And then there is no L1 invariant function. Now, also T1 is associated with finding these dual elements, if you like, but it's not exactly the way we find them. We find them by appealing to the theory of, theory which is similar to the theory of automorphic forms. Maybe not exactly automorphic form theory, but quite close to it. And the relationship with this Perron-Frobenius operator is expressed in these two equations. So you solve these two equations, you find these Hn plus and Hn minus, and you recover these functions H sub n and M sub n. And you do it on the unit interval, but then outside, how do you do it? You do it by formulas like this, how to extend. This formula tells you if you have Hn inside, you have Mn outside, and vice versa. Okay, so it's enough to have the function on the unit interval -1 to 1. Okay. Okay. Let's see. How are we doing here? Any questions?
I don't
No
have,
questions.
okay.
Just hard to understand.
There is a question in the chat.
There
Uh-oh.
is. Let's see. Where is it? Let's see. I will look now more. Yes. Where to find it? Chat. Yes. Let's see. Does your representation, can it be used to obtain explicit solution? It cannot be well written using the Fourier transform. Aha. I would say that this representation is very strongly related with the Klein-Gordon differential equation. So it fits with that, but it also, the approach fits with the need to use data like F and its Fourier transform along sparse sequences. So it's also related with that. Yes, can I do? No, it's not supposed to. I think I should send it to all, everyone. Yes. Yes. So you, if you take F and its Fourier transform, if you know F everywhere, then you have I mean, that's enough. You know your function. But suppose you don't know the function everywhere, you just know it along some sequence. On the other hand, maybe you also know the Fourier transform along some other sequence or the same sequence. Then is it possible that you can recover your function? It turns out that it is possible if you started with the test function. And this is from the work of Radchenka. (2019). So you take a function, you take its Fourier transform. Suppose that you know these things on plus minus square root of 1, square root of 2, square root plus minus square root of 3, and so on. Do you know the function? It turns out you know the function if you have that. This is quite a surprise, in fact. People have studied earlier this issue of knowing the function and its Fourier transform along more massive sets. And we studied how massive do these sets have to be able to determine the function. To have such a very sparse situation where it seems fairly new. And it was okay. Let me also say that there is a relationship, there's a connection with sphere packing. Okay.
There's another question in the chat.
Yes, yes, it's possible to obtain such a representation with other transformations, not necessarily hyperbolic. What kind of, you mean Möbius transformation or something?
I don't know, but just replacing your first transformation 1 over x by another, I don't know.
It might, well, you can try. Maybe it will work. Depends. But this particular one is related with PDE, which makes it more interesting, I think.
Okay, but my question was in relation with PDEs. If you can do it with other transformations, maybe you can solve other type of PDEs.
Well, yes, maybe, yes. I think they should be connected with some kind of expressions that are natural. They should be some kind of rational expressions, I think. Otherwise, it's and yeah, it should fit in a nice, natural way. I'm not sure that it will be easy. Maybe there is a way, but I think that it's some kind of theory which is between, which is hyperbolic, some kind of hyperbolic theory, which is a little smoother than the wave equation. The wave equation is terrible, although the solutions are easy to describe in this two-dimensional setting. But the wave equation is quite terrible. The solutions are not well behaved, and you don't get good theories like this. So there is some kind of smoothing effect, which is not seen at the level of the functions of these solutions of the Klein-Gordon equation, but some kind of smoothing effect that still forces such uniqueness theorems. Also, there is a paper which maybe I can't share that one. Let's see if I can do that. Okay, maybe I go here. I could try to share. Can you see it?
Yes, we can.
Excellent, good. So this is a paper related with this topic. It's not exactly this topic, but it's connects these things. So especially with radial functions and the Fourier transform of radial function, and how to get the uniqueness from our theorem, basically with Alfonso, this kind of our method at least. So the approach here in this paper is working with Gaussians and taking Fourier transform with Gaussian waves. And then we know how to take Fourier transform with Gaussian wave. This is a well-known thing. And you have such a formula. So taking a Fourier transform of waves where you have added lots of Gaussians, you can calculate the Fourier transform too, and it's again an integral of Gaussians. And then no, there is a trick here, and with the integration by parts, and this integration by parts allows you to connect with this work I have with Alfonso earlier. So, for instance, if you take we have this theorem 1. If you take a psi function, which is L1 in the real line, and capital psi as above, what is capital psi is this function. where we integrate and get Gaussians, and we have a factor in front to create a little bit of singularity at the origin, but maybe not so important. And if the function psi and its Fourier transform vanish on all integers in Z4, and this is, so we work in 4 dimensions, and if the behavior is at least not too terrible at the origin, then the function is, this little psi is in H1 in the upper half plane, and as a consequence, your function capital psi is 0. So that's the kind of thing that happens in, so it connects nicely the behavior on spherical, well, radial functions. So the behavior along the spherical shells of functions and their Fourier transforms. Okay, then there is a generalization to other even dimensions, which is a little tricky. I guess I could recommend you to read these things if you find the topic interesting. And then the whole thing boils down to working with weighted transfer operators and doing this slightly generalized ergodic theory that we worked out with Alfonso in the previous work. Okay, I think my time is I'm getting close to, let's see, does there exist for domain for which is bounded? Ah. This I don't know. At least not a simply connected domain. Maybe a really bad domain with lots of holes. Okay. So I'm maybe a little bit far away from Bergman spaces, but it's something I find interesting. So I want to share it with you guys. Bill?
Yeah? Are
Are you there?
Yes, I am.
I think I'm finished more or less. I gave some idea, some topic that I found interesting. And
Well, let's
I
thank
think we're
Håkan for an engaging talk. So thanks. All right, so I'll manage the questions. So just shout them out or put them in the chat. I think it's easier at this point if you just interrupt with a question.
Håkan, the paper you shared, is this the main resource for this topic, or there are other?
we'll have another paper coming out soon.
Okay. We keep our eye on archive.
But there is this paper also available if you like, and it shows the connection.
Sure.
Håkan, there's been a request for you to upload your slides to the chat. I don't know if you know how to do that.
No, not necessarily, but maybe if you help me, Bill, I will be able to do it.
How about email them to me?
Okay, and I can do it if, let's see, if I have your email address, then I can do it.
Ross@richmond.edu.
Ross?
Ross, W-R,
W. Ross.
@richmond.edu.
And no dots or anything?
You know what?
No dots or anything?
W. Ross @richmond.edu.
Not W. Point Ross or something?
No, just W. Ross.
Okay, W. Ross @richmond.edu. Yes, right. I did it. And then I have to write file. And now we have to find the place. I'm looking. Yes, there. Yes.
All right, I am looking for it in my email.
Yes.
Float across the ocean.
Yeah, there it is. Yes, open it. I send it to you in a moment. First, you must download it now. Yes, I think I sent it.
All right.
Maybe you already got it.
I am looking for it. All right. Well, anyway, while I'm waiting for that file,
Yes.
are there any other questions? As soon as I get it, I'll put it in the chat. But are there any other? Oh, I have it right here. And now,
Maybe it was just impossible to follow. So that's the end.
I have the file. Okay, I am going to put the file. I think I can attach something. I can attach a file. I don't know why I'm narrating this, but okay. Okay, so it's there. So anyway, does anybody else have any other questions they'd like to ask?
I can say also that, well, this operator T1, it can be defined on the Bergman space. So the spectral theory on the Bergman space could be interesting.
Okay. All right, so I don't hear any other questions here. So let's thank Håkan again, and you can download his slides from the chat. All right, so our next talk is at noon.